Hello everyone, and thanks to the organizer for this invitation. My name is Sabine Süsstrunk and I'm a professor at EPFL. As this workshop is about images across domains, I chose to present a family of techniques which are applicable to many imaging domains and imaging tasks, namely Superpixels, Supervoxels, and our newest algorithm, Adaptels. Superpixels and Supervoxels have been around for a while, but they are passing the test of time even in the area of deep learning, computer vision, and image processing. And they're especially useful in situations when labeled data is missing or sparse and computational efficiency is required. So that you know who's talking to you, here's a more or less recent picture of me taken in the happy pre-COVID times. And here's a picture of Radhakrishna Shanta, my brilliant former PhD student and postdoc, and still brilliant close friend and colleague. He's the main architect of the work I'm presenting here. Superpixels are areas in the image that result from oversegmentation. The term was first coined by Wren and Malik in Learning Classification Models for Segmentation, CVPR 2003. So as I mentioned, they have been around for a while. Compared to naive segmentation, that gives you segments that are small and large. So on the left-hand side, you see these small segments, but then you of course see also the very large segment here in the background. Superpixels are relatively small, and they contain similar pixels, as you can see here on the grass or in the background. They're all roughly of similar size, and they adhere relatively well, although not always, to the object boundaries. So hopefully you can see it here. In this superpixel we actually still have part of the nose and the background because their color is so similar, the color of the pixel is so similar within the same superpixel. In addition, superpixels have limited adjacency, and most superpixel algorithms let you control the number of superpixels. So why do we use superpixels? Superpixels provide a convenient primitive from which to compute local image features. They capture redundancy in the image and greatly reduce the complexity of subsequent image processing and computer vision steps. They have proved to be very useful for many imaging tasks across multiple application domains, and they are still very much in demand when deep learning techniques are not applicable, or even in conjunction with neural networks. Let me show you a few examples across imaging domains. Here, superpixels are used to spatially aggregate features for hyperspectral image classification. Why? Well, superpixels simplify by aggregating similar features. Here we're using supervoxels, which are 3D extensions of superpixels. We use them in the segmentation of mitochondria in EM image stacks. Why? Well, the graph-based segmentation was cheaper based on supervoxel than just doing it on voxels. Here we're using superpixel for salient object detection. The saliency is calculated per superpixel across multiple scales and then combined. And then why again superpixels? Well, it's cheaper to train the CNN and cheap to assign saliency to entire superpixels instead of pixels. So as I mentioned before, superpixels and supervoxels have their applications across multiple imaging tasks and multiple domains. Here is a list of imaging domains our first superpixel algorithm, SLIC, was used in. It shows the citation count per field according to Scopus. Of course, we have predominantly computer science, i.e. computer vision, where there's lots of application, of course, in tracking, 3D, body movement estimation, foreground, background subtraction, salience, you name it. Then we of course have remote sensing, we have medicine as we showed before, but there's also actually a surprising number of citations in mathematics. And under the category other, you actually find fields like economics and social sciences. So how do we create superpixels? We propose two methods, SLIC, as in simple linear iterative clustering. You just saw a very popular superpixel method, and SNIC, its non-iterative version. Both SLIC and SNIC use local k-means on the image plane, or in case of voxels, on the image stack. We define the cluster centroids in LAB color space, but that's not strictly necessary. You can actually get a relatively good result just applying it in sRGB color space on a square grid. The distance measure we use is a combination of spatial distance and color distance. Again, the spatial, it's actually the Euclidean spatial distance and the Euclidean color distance. The spatial vector x here can be of 2 dimensions in case of superpixels or 3 dimensions in case of supervoxels. And the Euclidean color distance, of course, is delta E if you can calculate the distance in CLab. The superpixel size is the square root of the number of pixels divided by the cluster. And the compactness factor m equals to 10 was basically empirically found to be best. Now, to make the clustering more efficient, SLIC searches only over a neighborhood of 2 times s, where s is the size of the superpixel. And here is the result of SLIC given different numbers of superpixels. So even though SLIC is extremely popular, it does have some drawbacks, such that it needs several iterations. It actually repeats computation in overlapping regions. It needs quite a bit of memory to store minimum distances from a centroid, and the pixel connectivity is only enforced during post-processing. For these reasons, we actually developed SNIC, which has 2 modifications. First, the centroid evolves using online averaging, and second, we use priority queue base label assignment. I refer you to the paper for more details, but I'm just going to show you an illustration how non-iteratively SNIC actually creates the cluster. You can see with more growth how the orphan pixels actually disappear. Last, I would like to present our newest algorithm, namely Adaptels. We were inspired by this because there is a drawback with the conventional superpixels that enforce those size uniformity. It does not always really adapt to the image content. So depending on the image region, here, the background here, sometimes you have just too many superpixels, like in the background here. When you choose them larger, it's okay for the background, but as you can see in the middle image on the dress, you just have too few. You do not actually capture the details of that region. So it's not always trivial to choose the right number of superpixels. And so we developed a method that adapts to the image contents, which we call Adaptels. And here you can see on the dress we have smaller superpixels, also partly in the hair, and in the background we have larger ones. So how do we do this? Well, we start with a pixel and its neighbors that have the same color. Then we add pixels in the increasing order of the color distance from the average color of the adaptel. And then the adaptel terminates when the accumulated sum of all color distances exceeds a user-provided threshold. So the whole algorithm has just one variable, and that's that user-provided threshold. The pixels at the boundaries of the previous adaptal serve as new seeds. And then we grow these adaptals, and these new adaptals also terminate when the accumulated all color distances exceeds the user-provided threshold. Note that the new adaptals may take pictures belonging to a previous adaptal if the distance is smaller. And let me now illustrate that to you again, how this looks like. And recall, there's only one parameter, and that's user-defined threshold. And we actually found that a threshold of 60 does quite well for many, many, many imaging applications. Let me give you another example once this is done. Starting off actually with smaller adaptals in the middle, and then larger ones in the background. As with SLIC and SNIC, it's actually trivial to extend this to image stacks. Here is an example of a video which you can actually calculate the super adaptals, adaptals, Adaptvoxels, or whatever we want to call them, over different frames. So a few parting notes. Use Superpixels or Supervoxels when there is need to simplify. As we said, you can actually gain about 2 orders of magnitude in reduced complexity, which is extremely helpful, of course, if your algorithmic complexity is higher than ON. Also very helpful to use Superpixels and Supervoxels when your input is noisy. You could calculate your superpixels using deep learning method, and it has been done. But in my opinion, introducing complex method to create superpixels defeats a bit the purpose of superpixels. It's a pre-processing step used in many imaging tasks afterwards. And it doesn't have to be really that complicated. There might be some applications I'm not aware of where it is, but usually, when in doubt, use SLIC. It has been proven over time that it is actually quite powerful. And keep in mind, really, the differentiating factor at the end to use superpixels is efficiency. Thank you for your attention. Here are the links to the code for the different papers.